Good evening. My name is Mark Barnico, and I'm the Executive Director of the University of Chicago, Francis and Rose Yuen campus in Hong Kong. Thank you for joining the program this evening. This is the first program of our Yuen campus Director's Pick series of this year in 2023. This evening, we're going to peer into the unknown with new insights from the James Webb Space Telescope from our faculty from UChicago. I'm really excited about this program. This has been a long time in planning. As always, we're sharing tonight's program live via Zoom, Facebook, and YouTube from the UChicago Yuen campus in Hong Kong. If you have questions for our experts tonight, you can submit them through the questions and answer button by first registering on Zoom. And I always would like to remind you that if you want to keep up with all the activity that's going on the Yuen campus here in Hong Kong, you can check out our website at www.uchicago.hk. and subscribe to our e-news, and we'll send you news about all those activities, programs, information. Or you can also follow us on the Yuen Campus Hong Kong social media accounts on Facebook, Instagram, Twitter, and LinkedIn. As usual, we'll wrap up tonight's program with a poll and more information about upcoming events, so please stay tuned to the very end. The James Webb Space Telescope is the largest optical telescope in space. It consists of 18 hexagonal mirrors, a sun shield, and is equipped with high resolution and high sensitivity instruments. It orbits more than 1 million miles away from Earth, much farther away than the Hubble telescope. But, I'm not an expert. We have our experts here tonight. And so I'd like to first introduce our moderator for this evening, our faculty director for the UChicago Yuen campus here in Hong Kong, Ken Pomeranz. Ken's a distinguished university professor of modern Chinese history and in the college. Professor Pomeranz's work focuses mostly on China, and he's also very interested in comparative and world history. Most of Ken's research is in social, economic, and environmental history. He also has worked on state formation, imperialism, religion, gender, and other topics. Thanks for joining again tonight, Ken. We really appreciate you moderating this program and bringing our speakers together. I know that was challenging given the demands that they have on their time. I'll hand the stage over to you, and you can introduce our panelists, and I'll come back at the end and close out the program.
Thank you very much, Mark, and thank you everybody for being with us tonight, if you're in Hong Kong or whatever the time zone you're in today. I want to start by giving a brief introduction to our two speakers tonight. They're both core members of the James Webb Space Telescope program, and I would note that they're at the two far ends of the things that the telescope helps us with, one exploring relatively near things in space and one exploring the most distant. And it says something about the power of the telescope, that it's important in both those areas. So holding down the close end of things, we have Professor Jacob Bean. Professor Bean is a professor of astronomy and astrophysics here at the University of Chicago, and he co-leads one of the Webb Telescope's early release science projects. He also conducts observational studies of planets beyond our solar system with ground and space-based telescopes, including the Hubble, Magellan, and Gemini telescopes. And he's especially interested in studying planets around low-mass stars and in probing the atmospheres of the smallest known exoplanets. Earlier in his career, he helped characterize the atmosphere of a super-Earth planet orbiting another star for the first time, and the work was an important milestone on the road to identifying potentially habitable Earth-like planets beyond our solar system. So thanks very much for being with us, Jacob, and you'll be speaking first tonight, but I think I should introduce both our speakers, so let me go on. Our second speaker will be Professor Michael Gladders, also from the University of Chicago. He's a professor in the Department of Astronomy and Astrophysics, as well as in the college. He's part of a science team tackling early Webb telescope observations. He's also involved in the Dark Energy Survey, the Magellan telescopes, and the Giant Magellan Telescope. And his research revolves around instrumentation and observational astrophysics, extending from the galactic to the extragalactic, dealing with some of the most remote and faint signals we can receive. So thank you very much, and let's get underway. Yield to the experts.
Good morning from Chicago. Good evening for those of you who are in Asia. My name is Jacob Yuen, and as mentioned, I'm a professor in the Department of Astronomy and Astrophysics at the University of Chicago. And I'm going to be kicking off our session talking about science from the James Webb Space Telescope. And I'm going to be focusing on something that's close to us, extrasolar planets, planets orbiting nearby stars. The James Webb Space Telescope is NASA's latest flagship space telescope and mission to probe the cosmos. It was launched a little over a year ago on December 25th, 2021. For those who celebrate, that's Christmas Day, and that's a very special, holiday for a lot of people in the West. It was a very special Christmas present for astronomers to receive this extraordinary new facility. It was a flawless launch, a very beautiful launch. And a really exciting moment for all astronomers who had really been waiting for decades for this new facility. The story for this facility began in the late 1980s, and I'm showing here a cover of one of the first reports that outlined what came to be the James Webb Space Telescope. It was originally called the Next Generation Space Telescope. And back in the 80s, this was before even the Hubble Space Telescope had been launched. There were a couple of concepts floating around for what the telescope could look like. On the bottom right, you can see the concept for having the telescope actually on the surface of the moon. And then the upper right, you can see a concept for an actual telescope floating freely in space. After a number of decades of work, the James Webb Space Telescope concept crystallized, and this is an artist concept of what the telescope looks like. As mentioned, 18 gold-coated hexagonal mirrors to create a primary mirror 6.5 meters across, a large tennis court-sized sun shield to keep the telescope cold, and then also associated electronics, communication equipment on the other side of the sun shield. For comparison, James Webb is substantially larger than NASA's previous flagship space telescopes. You're probably familiar with the Hubble Space Telescope, with a primary mirror diameter of 2.4 meters. But James Webb is also sort of the intellectual successor of a mission known as the Spitzer Space Telescope, which is primarily observing in the infrared part of the electromagnetic spectrum. That was an even smaller space telescope of 0.85 meters in diameter. So you can see that James Webb was really a dramatic advance in terms of the size, which it translates directly into a dramatic advance in the sensitivity and resolution of the space telescope. Now, I showed you an artist's concept of the space telescope, and I show it here again on the left. And the reason I'm not showing you a real picture of the space telescope is because, remarkably, on the ground, when the telescope was built, it was never fully deployed. No, all of its components, the sun shield and the primary mirror, were never fully deployed all at once. The telescope was designed to launch into space on the tip of a rocket, and therefore it had to be folded up like origami to sit on top of that rocket and to sit in the fairing at the tip of that rocket. And so you can see a real picture of what the space telescope looked like, fully folded up and ready for launch. The secondary mirror boom is folded up. The primary mirror is folded into three main pieces. The sun shield is rolled up and stowed, and everything is folded up to fit into a fairing on the tip of a rocket that's only a few meters in diameter. Following the launch on Christmas Day in 2021, Webb's journey into space was far from complete, and astronomers' nervousness was far from over. Because the telescope had to be folded up for launch, it then had to deploy while it was in space. So for the next 30 days following the launch, Webb was making its journey out to what's called the second Lagrange point, or L2, as known for short. This is its place in space about 1.5 million kilometers beyond the Earth, out beyond the orbit of the moon around the Earth. A stable place in space where it could perform its astronomical observations fairly undisturbed. That journey took about 30 days, and during those 30 days, there were a number of deployments of the telescope, 50 major deployments in total to unfold and unfurl the telescope. Astronomers had these numbers sort of memorized, and over the course of this journey, NASA would regularly release updates about how these deployments were successful. And every time there was a successful deployment, astronomers collectively breathed a sigh of relief. There were 178 mechanisms that all had to release flawlessly for the telescope to become fully deployed and operational. It involved a quarter mile of cables alone just to unfurl and tension the sun shield to keep the telescope cold. Following that, there were another 5 months of commissioning operations to, for example, align all these hexagonal mirror segments to create a sharp image. This is JWST's first light image from February, about a year ago. And this is an image of a single star. And there are 18 different images produced by 18 different hexagonal segments. The mirror segments were stowed for launch so that they wouldn't be damaged by the vibrations of the launch, and then released, and they needed to be aligned to create sharp images. And so this is the first science image, and you can see the mapping of all those individual images to the individual hexagonal segments. At this point, the telescope is not even a telescope. All those mirrors are operating independently, and they need to be brought together to operate together to produce sharp images. Well, about a month after that, the engineers working on the Webb telescope were able to align the images from those different mirrors and phase them up and to create these amazingly sharp images. This is an image of a single star now, created with all the mirror segments working in concert. And you can see in this image the sensitivity of Webb. All those little points of light in the background of this image of a nearby star are galaxies. And the sensitivity of this image likely rivaled the best images ever obtained with the Hubble Space Telescope before. And this was simply a calibration image. Following another few months of commissioning where all the instruments were turned on and tuned carefully to give scientific results, Webb finally released its first science-ready data products in July of last year. And so this is one of the images that were released at that time, showing a beautiful nebula of gas and dust, and showing Webb's real sensitivity in the infrared to be able to peer through this kind of nebula. The work that I do is probing the atmospheres of extrasolar planets. These are planets that orbit other stars, and I like to study the atmospheres of these planets. And so I look at the nearest planets, the planets orbiting the nearest stars. One of the teams that I'm involved in, a 300 plus member collaboration that spans the entire globe, was able to get data from James Webb for an exoplanet atmosphere starting just a few days after these first scientific data were released. Now, when we study the atmospheres of extrasolar planets, there's a couple of different kinds of questions that we're trying to answer. For one, we're just trying to answer, what are these objects like? We've been able to detect thousands of planets orbiting nearby stars, but for most of these planets, the only things that we know about them are, say, their masses, their radii, and how far they are away from their star. So really, they're just sort of anonymous points on a scatter plot that astronomers use to make statistical inferences about the occurrence of different kinds of planets. But if you look at the planets of our own solar system, you see they have remarkable different phenomenology. And so that's the questions that we're trying to answer for the atmospheres of extrasolar planets. What are they like? They experience different temperatures. They have different gravities, different compositions. They have different chemistries as a result of this. And what are the chemistries of those planets? We're also interested in understanding where these planets came from. The atmospheres of planets are a fossil record of how the planets formed and evolved. And so by measuring the compositions of the planets, we can gain a deeper insight into the formation of planetary systems. The observations that I do focus on transiting exoplanets. These are planets that eclipse their host star. They pass along our line of sight once per orbit between the host star and us. And so we do a so-called combined light observation of these transiting planets. We don't spatially resolve the planets from their host star, but we observe them changing the light that we get from the system as a function of time. So when the planet passes in front of the star, for example, when it transits the star, it blocks some of the starlight. Some of the starlight also filters through the limb of the planet's atmosphere and imprints the properties of the planet's atmosphere on the data that we're getting. And so by making measurements in time, we can resolve the planets from the star rather than resolving them spatially. So I'm going to show just a couple examples of some of the data that we've been able to get with James Webb to show some of the breakthroughs that we've been able to make. I'm going to focus on observations obtained in transit. So this is observations of a fairly anonymous gas giant type planet that was just chosen for first observations because it was very easy to observe. The signals that we expected to get were quite large. Now, we got data just a couple of days after the first science data were released from James Webb. And so the last 8 months of my life have really been the most exciting part of my scientific career, probably ever, seeing these data for the first time. It was really kicked off last July. We were able to analyze and make progress on the data fairly quickly because we were working together as a very large international team. And so this is just an example of one of the first results that I saw from this big program that I'm co-leading, where we've detected the signature of carbon dioxide or CO2 in the atmosphere of a planet. This is a picture of someone's laptop who is at a workshop, just sort of illustrating the interesting way that science works in our interconnected world these days. So this is the first detection of carbon dioxide. And just to put this in context of the kinds of data that we had before, I'm showing here a comparison of the James Webb spectroscopic data in red overlaid across the photometric data from the Spitzer Space Telescope that we had before. And this photometric data has very coarse wavelength resolution. And we had hints that there was CO2 absorption in the spectrum of this planet before, but it wasn't until we had these spectroscopic data that were allowed to really spectrally resolve and detect this smoking gun signature of carbon dioxide in the planet's atmosphere. So you can see here the dramatic increase that's been enabled by James Webb. More spectral resolution, greater sensitivity brings out new features in these planets' atmospheres. This is a more scientific plot from a first paper that we wrote just a couple of weeks after getting these data. It was a really intense period working quickly on these data to gain our first insights. And so this is the first detection of carbon dioxide. In these kinds of plots, the absorption from the planet's atmosphere makes the planet look bigger. So absorption is up. And so this bump here that you can clearly see is highly statistically significant, something like 25 sigma statistical significance, is due to primarily carbon dioxide in the planet's atmosphere. We create sophisticated models for the planet's atmosphere that compute the temperature and the chemistry and calculate how light traveling through the planet's atmosphere will be absorbed and will change the appearance of the planet. And we can match those to these data and then gain inferences back out about what the planet's atmosphere is like. Now, in these data, which were matched by fairly nominal models for the planet's atmosphere, there was an unexpected discovery. CO2 was a fairly expected thing, but had never been seen before for an exoplanet. But we also saw this extra bump that wasn't matched by these nominal models. And after a little bit of work, we were able to realize that this was an additional molecule that had never been seen in exoplanet atmospheres, known as sulfur dioxide, or SO2 is its chemical formula. SO2 is a more minor species in planetary atmospheres. On terrestrial planets, it's actually produced by volcanic activity. This is a gas giant type planet. And SO2 is actually produced by a process known as photochemistry in this planet's atmosphere. Photochemistry is the interaction of high energy light from the host star altering the chemistry in the atmosphere. So this bump was easily explained by SO2. And SO2 itself would arise from a photochemical process that began with actually the destruction or the splitting apart of water molecules. This cartoon picture here shows the series of chemical steps that we think are taking place. High energy photon does what's called dissociation of the water molecule, breaking it up into a hydrogen atom and an oxygen and a hydrogen atom combined. in successive chemical processes involving the stripping of hydrogen off of another molecule known as hydrogen sulfide and the oxidation of those free sulfur atoms that were produced, ultimately produced this sulfur dioxide. Now, this is exciting because photochemistry is a fundamental part of planetary atmospheres. In our own Earth's atmosphere, photochemistry gives rise to ozone that's in the upper part of Earth's atmosphere. And the ozone protects life on the surface from high energy radiation from the sun. Photochemistry had never been seen before in an exoplanet atmosphere, and it will be important to understand it in our search for life on other planets. This is the first time that we've ever seen it, and James Webb enabled that. To give you a sense of how the data have progressed, I'm showing here now a complete spectrum of this planet. We observed it with multiple instruments on James Webb, and we've put them together into this very rich spectrum. It looks a little bit noisy to you, but that's because there are many, many molecular features that we're seeing here in the data. Different atoms and molecules, and even the signature of inhomogeneous clouds on the limb of the planet. I want to also talk to you about a different way to observe transiting exoplanets and show you a little bit of data that we've been getting for this kind of geometry. If we look at the planet, at the light the planet itself emits, we can map that when the planet goes behind the star at secondary eclipse, and also as the planet orbits the star. These planets that we're observing have a permanent day and night side due to tidal forces with their star. And as the planet orbits, what we're seeing as observers is this planet actually rotating on its axis. So we've used James Webb as well to make a temperature map of a planet known as a sub-Neptune sized planet. This is the first kind of temperature map that's ever been made for this type of planet. From what we understand of planet occurrence rates, this is the most common kind of planet in our galaxy, and we've never been able to observe its atmosphere like this before. What you're seeing here is a long time series of observations beginning before the planet passes behind the star, which you can see here. Hopefully you can see my mouse cursor. Continuing half an orbital period later to see the transit, and another half an orbital period later to see the secondary eclipse. The orbital period of this planet is only 1.5 days. So by staring at this system for about 2 days, you can see a full orbit or rotation of the planet, plus a little bit more. And on the right, you can see the temperature map that we infer from this planet. We've learned that this planet is actually enshrouded by clouds that are highly reflective, and it also has an atmosphere that's enriched in heavy elements. Now, we're studying the atmospheres of mostly gas-rich planets so far with James Webb. But one of the questions that we also want to answer is, are any of the small rocky planets that have been discovered recently potentially habitable? And to do that, we also have to study the atmospheres of those planets. And so this is my final slide before I hand it off. I just want to come back to this first observation of a gas giant type planet and point out that CO2, carbon dioxide, is an expected molecule in the atmospheres of not just gas giants, but also rocky planets. We expect terrestrial planets to have CO2 in their atmosphere. And for planets that are a little bit hotter than the Earth and are orbiting smaller stars, the signals that we would expect to get from these terrestrial exoplanets are only going to be about a factor of 10 times smaller than the signal that we easily detected for this gas giant with the first James Webb observations. So if you can imagine taking this spectrum, but scaling the feature size down by a factor of 10, given the same errors and uncertainties, even for a terrestrial planet, we should be able to detect carbon dioxide. And so that's one of the things that we're doing moving forward now with James Webb, is we're expanding our observations from gas giant type planets, which we started with because they were easy, to smaller rocky planets, and now pushing towards planets that are potentially habitable. So I encourage you to keep your eye on the science coming out of James Webb, and especially the extrasolar planet science, as we anticipate exciting results also coming for rocky terrestrial planets. And with that said, I'm going to hand it over to Professor Michael Gladders, who's going to talk about now something at the very edge of the observable universe, distant galaxies in their youth.
All right. Thank you, Jacob. And thank you for that view of exoplanets. Every time I hear you talk, it's something new and interesting and fascinating and really, really good stuff. Okay, so let me just get my talk going here. You'd think after years of Zoom on the pandemic, I would be an old pro at this. Let's see. What's happened? All right, how's that? Good? All right. So, yeah, as Jacob said, I'm going to touch on a slightly different topic here. James Webb, of course, but James Webb working now in the very distant cosmos, which is mostly where my research effort goes. The background image here, just to kick things off, it was one of the first publicly released images from James Webb in the early days of July. There was a major press announcement from the White House, and this was one of the images that was shown. It shows a cluster of galaxies. You see all those white fuzzy specks are galaxies within the cluster. And then you can see all these oddly distorted arc-like features. Those are all distant background galaxies that have been gravitationally lensed by the extreme mass of that foreground cluster, which has created sort of this halo of distorted and magnified images behind it. I point that out now because a lot of what I'm going to talk about exploits gravitational lensing scientifically. So as I come to the end of what I'm going to tell you, you'll see this idea again. But before I jump into the sort of science side and looking at distant galaxies, I want to have a little look at another aspect of the telescope. So Jacob gave us a really good sort of review of the launch of the facility, how it got to where it is, the telescope itself, how it unfolded, which really was the most extraordinary month to watch as a very interested eventual user. I want to show you what happens once the light hits the telescope. And all right, for some reason, my computer, there we go. Okay, so this is what you get in 10 minutes with an astronomer doing the cartoon instead of NASA's graphic artists. You know, photons come into the James Webb basically like this. Okay, they bounce off the primary, they go up, bounce off the secondary, and then disappear down a hole down the middle of the primary to the other side. To show you that once more. And of course, what happens down there? Well, that's where all the magic happens, as it were. So this is the picture that you often see in artist rendering of James Webb. It's a particularly good angle. The person who made it had some training in photo composition, etc. They don't show you this picture. Oh, before I go on, I should say and remind you that sun shield there that you see, that multi-layer thing, which is the size of a tennis court, is designed to do one real thing, which is to ensure that the telescope side of this structure sits in perpetual darkness and hence cools to very low temperatures, about 40 Kelvin, about 40 degrees above absolute zero. So that side of this facility is cold and dark. And then the other side, where the spacecraft bus and everything is in sunshine, it's bright and warm. Now, another view of this that is less often shown is this. So this is just looking from a different angle. And here now you can see all the stuff on the back end of the telescope, all that stuff there. And that's where all the instruments sit. That's where the light goes once it disappears down the hole in the primary and then gets fed into the various instruments, of which there are 4. Working basically from 0.6 microns down to about 28, 29 microns. Now, I'm not going to talk in detail about all of these, but I am going to show you data from 3 of them, these 3, and I will give you a brief description here of each of them. So just in text, we basically have on James Webb a near infrared imager called NIRCam, which works from 0.6 microns to about 5 microns. And this is primarily used to take direct images. There's a few other little things that it does, but this is its primary function, using a wide range of filters to sample a whole bunch of different wavelengths. James Webb met and exceeded its design for optical quality. And as a result, at the blue end of NIRCam's range, it produces images that are about 2 times sharper than those that we get at best from the Hubble Space Telescope. And so this is now basically the sharpest imaging that we have available as astronomers. In addition, and complementary to NIRCam, we have NIRSpec, very inventive names, which basically works over the same wavelength range, taking spectroscopy. You've seen a little bit of data from NIRSpec from Jacob's talk. An interesting thing about NIRSpec is it uses a whole bunch of different configurable front ends. Sort of the classic astronomical spectroscopy, you put a slit, a long, thin aperture on some object, say me, and you record light through that slit. And NIRSpec has those fixed slits. But in addition, it has something called an integral field unit, where you have a whole bunch of slits stacked on top of each other that are fanned out across the field of view of the instrument, which allows you to take spectra at all of those locations at once and basically get spectroscopic information fully spatially filled over a small square. It also has a configurable multi-slit module where you can take spectra of many individual objects in the larger field of view all at once. The other main instrument, MIRI, combines imaging and spectroscopy in one. And it goes basically from 5 to 28 microns with comparable spectral resolutions to NIRSpec. It also has an integral field unit and fixed slits. But the reality is for MIRI, the James Webb sort of notional in the shade temperature of 40 Kelvin is too hot. Okay. And so MIRI is actually actively cooled down to about 7 Kelvin, i.e. 7 degrees above absolute zero. It's quite a cold place. So if we want to talk about the study of galaxies, it's worth understanding sort of how we have come to understand galaxies. 100 years ago, we were debating, well, I wasn't alive, but others were debating whether galaxies were even a thing. There's something called the Great Debate, where people in 1920 the conversation was, is the Milky Way, which turns out to be the galaxy that we live in, the whole universe, or are the nebulae, as they were just called then, that people saw other Milky Ways at greater distances? That turns out to be the answer. But we've made enormous strides from that time a century ago to where we are now. We've done much of that observational research over a wavelength range of about 0.32 microns to 2.5 microns. That's basically the range that you can access from the ground. On either end of that range, the atmosphere becomes too opaque in the blue and too bright in the red. The Hubble Space Telescope has broadened that range a little bit, at least to the blue. But the Hubble Space Telescope actually doesn't go even as red as the facilities we use in the ground. And that's because the Hubble Space Telescope is in low Earth orbit, and it goes around the Earth about once every 90 minutes. And every 90 minutes, it goes bright sunshine, shade, bright sunshine, shade, and its temperature is fluctuating by hundreds of degrees. To flatten out those fluctuations, which are quite destructive to the facility, the telescope is actually actively warmed. And that means the Hubble Space Telescope is warm enough that beyond about 1.7 microns, we can't even get reasonable data because thermal signals swamp the signals that we're after. And there's been other much smaller facilities, Spitzer, for example, as Jacob showed you. But the reality is a lot of what we know about galaxies comes from a fairly narrow wavelength range. And in particular, rest wavelengths of about 0.9 microns down to about 0.09 down to about 0.9 microns. Most of that's accessible from the ground. The so-called optical wavelengths are particularly rich in diagnostic information. And you can sort of see this here. And just to translate, because optical astronomers often talk in angstroms, but James Webb, going much longer wavelengths, and we're really using microns as the unit. Just to translate those units, divide by 1,000. So these two spectra are of galaxies nearby, taken from the ground. And you can see that there's an enormous amount of detail in these spectra over sort of optical wavelengths from 0.4 to 0.9 microns. And different galaxies, as you can see, look entirely different spectrally. But all of those galaxies nearby, they're the product of about 13 billion years of star formation and structural evolution. The galaxies in our neighborhood, including our own Milky Way, are large and mature, albeit very interesting, systems in which the past record of how they came to be, how they formed and evolved, is quite difficult to discern. So, it'd be nice if we could just go and look at younger versions, and it turns out we can, because observational astronomy has basically the best time machine available. So the reality is, when you look out into the universe, you do not see it as it is now, in your now. You see it as it was when the light left the object you were looking at. In conversation with your colleagues across a room, that delay is nanoseconds, indiscernible. On a Zoom call around the world, it starts to become discernible. But, if you look out and look at the sun, don't look at the sun, it's dangerous, but, glance at the sun, you're seeing the sun as it was 8 minutes ago, not as it is now. If you start going outside our solar system or outside our own galaxy, if you go to the nearest large galaxy to us, the Andromeda galaxy, which is so close to the Milky Way that over the next 3 billion years, our galaxy and the Andromeda galaxy are going to collide and merge. Even at that very nearby galaxy, you're looking 2.5 million years into the past. Okay, so observational astronomy is a time machine. And if you look far enough away, we look almost all the way back to the beginning of time and space in the Big Bang. But there is this complication. Our universe is not static. The universe is expanding. And the light that leaves those distant objects expands right along with it. Basically, what happens is photons in an expanding universe have their wavelengths stretched by the expansion rate. And so as photons that leave an object early in the universe traverse the universe, their wavelengths get longer and longer in proportion to the expansion of the universe. And so then by the time we see them, those photons have been shifted very much to the red. This is fun, the redshift is what we call this. It's fundamentally really defined geometrically as it's basically due to the ratio of the current size of the universe to the size of the universe when that photon was emitted. Okay, and that's 1 plus the redshift. It has an observational consequence, which is that it stretches the observed wavelengths. Now, so that makes observing very distant objects through our cosmological time machine a little bit challenging, because this richness of diagnostic features that we see in local spectra move redder and redder and redder as we move to observing more and more distant, higher and higher redshift objects. So at redshift 0, the universe is 13.72 billion years old, and this sort of panoply of spectral features you see in this example spectrum have these observed wavelengths in microns. If I instead push this object out to redshift 1, well, those wavelengths double. And now we're seeing a significant amount of this information out in the near infrared, where we can still observe from the ground. The universe at this point is now only 5.9 billion years old. And if we push this out to redshift 2, we start to become limited in what we can do with current tools. So at this point now, the universe is only 3.3 billion years old. These spectral features are all now in the near infrared, and the redder half of these features are now lost to the Hubble Space Telescope, which basically cuts off at about 1.7 microns. So that grayed out piece, we can no longer observe these features with Hubble in any way. This redshift is about the peak of star formation in the universe. Earlier than this, the sort of average rate of star formation in the universe, averaged across all objects, was still increasing. It peaks at about redshift 2 and then has been slowly declining since. If we want to go back into those earlier times when the rate of star formation is still increasing, as galaxies are very actively building up, say going to redshift 3, much of this wavelength range where so much of our diagnostic information lies has become inaccessible. So we've lost most of it to Hubble, and even to the ground, which is limited at about 2.5 microns, we've lost the red end. We go out to now redshift 4, the problem becomes even more severe. And by redshift 5, we've almost completely lost access to any of this information with current tools. And by redshift 10, become important in the next slide, all of this information is inaccessible with any of our current tools. And it's really here at these redshifts, 5, 6, 7, 8, 9, 10, and beyond, that JWST was designed to really shine, to really give us a brand new view of the very early cosmos. And there was a really interesting recent result, not something that I was involved in, but worth showing certainly. This is just from the last couple of months. This is an observation. This is an actual observed spectrum of a galaxy at redshift 10.6, one of the most distant objects ever found, and certainly the best spectrum of such a distant object ever recorded. It's really, really quite remarkable. It's the result of about 6 hours of telescope time. It's simply an unachievable observation prior to James Webb. And in fact, we can see the whole range of wavelengths. That sort of red bracket at the end is what I showed you before. And then there's also some information in the rest frame ultraviolet, which you can see over to the left here. Take it from me, this is a really remarkable piece of data. Now, I'm involved with a number of James Webb programs, and like Jacob, I'm heavily involved with what's called an early release science program. This program is Templates, which is a long acronym I won't read to you. It's co-led by Jane Rigby at NASA Goddard, who I will note is this year's Brinson Lecturer at the University of Chicago. That happens in May. And Joaquin Vieira, who is these days at UIUC, who is also from the University of Chicago. He was John Carlstrom's grad student and graduated a little over a decade ago. And we brought together a sample of strongly lensed galaxies across 2 programs and combined them into this templates work and observed them with the three instruments that I described. Early release science programs have both technical and scientific requirements and goals. Basically, the technical goals are to put the instruments to test and work through data challenges and get that information out to our colleagues so that they can work effectively as well. And of course, the underlying scientific goals. And we have been very busy meeting both of those goals. I'll show you just sort of, just so you get a sense of how this works. Here's an example of one of the little technical pieces that we're dealing with. New instrument, all sorts of little challenges, unexpected and expected, that you have to deal with. One of the things we've been dealing with NIRCam imaging data is there is a noise source in the electronics that produces what's called 1/f noise. And when that fluctuating noise interacts with the readout architecture of the devices, you get this odd striping pattern in the raw data. And it's an interesting computational challenge to figure out how to remove that striping without accidentally biasing your observations of the objects of interest. And it's now basically a solved problem, but there was a fair amount of code writing that happened in August to get around this properly. Scientifically, here's the 4 targets that we're chasing. These are observations at 1 to 5 microns in the top row from NIRCam, and then 5 to 20 microns in the bottom row from MIRI. And the 2 on the left are from the South Pole Telescope project. These are dusty galaxies. Enormous amounts of star formation produce an enormous amount of interstellar dust. Interstellar smoke is probably a better way of describing it. So galaxies and that dust absorbs a lot of starlight and then re-emits it at longer wavelengths. And at those longer wavelengths, galaxies that are bright out there, and hence bright in the longer wavelengths of JWST, are dusty and typically have huge star formation rates. The 2 objects on the right, rather, were detected on the basis of their redshifted UV light, and they have very little dust. And so you might have expected in all cases that that these galaxies would look very different in James Webb, in the sense that the two on the left should get brighter and brighter as we go further and further red, and they sort of do. As you can see, this ring here is one of these lensed galaxies, and you can see in Miri it's much brighter. And you might have expected the ones on the right, you'd say, well, you know, they aren't very dusty. We knew that already. And so they should almost disappear as we go to Miri. And this one, 1226, does. But the next one over actually does something very weird. This is the first time this has been observed as well. You can see that these small clumpy structures in this lensed image, and by the way, this is strong lensing. So this is, your eyes aren't fooling you. This is a mirror image across a line basically here of a portion of a galaxy. This is a foreground star, by the way. And you can see this clump here at the ends as we go to the longer wavelengths suddenly starts to shine extraordinarily brightly. And that's actually due to very strong emission lines from what are called polyaromatic hydrocarbons, complex organic molecules that form in space around star-forming regions. And this has never been seen at this spatial resolution before, ever. This is the first observation of it. In fact, the observation of this target to the right was one of the images on the top, was the first science image that was taken by James Webb once it went into normal operations in late July. Okay, what are we getting out of this? Well, so here's two of these four objects. These are the ones from the South Pole Telescope. The South Pole Telescope, I should note, is also a Chicago project. John Karlstrom, who has just recently stepped down as the department chair, is the PI of that long-running program. And you can see here we have this is now spectral data. These are images at very specific wavelengths taken from this integral field unit spectroscopy of individual emission lines and their spatial structure. And the redder lines in particular, Passion Alpha in the middle there, that's the first time this has been observed at such a high redshift ever. And the bluest of the polyaromatic hydrocarbon lines at 3.3 microns below, ditto, the most distant detection of such a line ever. All of this is being worked into papers that are close to being submitted, I would say. Here's an example of one of the other targets from the Sloan Giant Arc Survey, which I've been running out of Chicago for sort of a decade now. This is the wide field image from NIRCam and a blow up of this little lensed object that has become known as the crab. You can sort of see why. Each of these little dots here, these are individual star clusters in this galaxy being formed at nearly redshift 3, whereas the sizes of some of these are less than 10 parsecs. Which is a ridiculously small scale to observe even with a space telescope. And it's only by combining strong lensing with this facility that we get to observe ththose scales. So another feeder program for what we're doing with JWST is this thing called Cool Lamps, which is a collaboration at the University of Chicago that I run based out of a course actually at the university, which we really first started teaching in January of 2020. We didn't know the pandemic was coming, but it came shortly thereafter. This is an undergraduate course designed to pull our undergraduate majors into serious research in a sort of course framework. It has a broader collaboration basis. Many of my senior collaborators are other institutions. We've had great success with it, with many discoveries by our students. And this is one of the most compelling. So this is from the first paper that this student collaboration published. This is Cool J 1241. This is a galaxy, this red arc here at redshift just beyond 5. It is the brightest known galaxy in the universe at redshift 5 or beyond. Just last year, we got some imaging of it with Hubble, which you can see here. And just a couple of weeks ago, the first data from our JWST program on this target arrived, and that's that right there. Now, this doesn't really do it justice, so let me zoom in a little bit. This is the James Webb NIRCam imaging of this target. This big arc is the lensed image of a galaxy at redshift 5.04. You can see maybe over here, this little sort of collection of dots. That's actually what we call the counter image. It's a much less magnified version of this galaxy, although still a complete image. And if you were to imagine that this galaxy weren't magnified at all, it would probably be comparable to a little blob like this down here, right? So remember that spectrum that I said was extraordinary? This arc is 160 times brighter than the object that produced that spectrum. Okay? And so in the next 6 weeks or so, we're actually going to start taking spectroscopy with James Webb's integral field unit on NIRSpec of the entire arc. And for every single one of these little clumps and lumps in this arc, we will get a spectrum comparable to that extraordinary spectrum that I showed you previously. And that will allow us to study not this whole galaxy, but individual tens of parsec-sized star clusters in it at a time when the universe was only a tenth of its current age. And that is going to be an extraordinary data set and an extraordinary journey. And maybe at some point in the future, I can come back and show you what came of all of that once we have the data. And I will stop there. And thank you.
Thanks very much to both of you. There's a lot to absorb. We have a bunch of questions, and I'm going to try to amalgamate some of them for purposes of time. And there are a bunch of them that basically cluster around the question of extraterrestrial life. So one person asks it in terms of the Fermi paradox, one asks in terms of the Drake equation. But the bottom line for all of them, I think, is, have we learned anything yet that shifts our understanding of the likelihood of finding extraterrestrial life? I'm guessing this is more a Jacob question, but either one of you feel free to chime in.
So yeah, I'll take this question. What we've learned over the last 10 years is that rocky planets in the habitable zones of other stars are remarkably common, okay? And the habitable zone of a star is the distance from the star at which a rocky planet with the right kind of atmosphere could have surface liquid water. We think liquid water is the primary requirement for life on a planet. That really sets the hunting area for where you should go looking for life. So we know that planets in those habitable zones are common. Around sun-like stars, maybe like a few tens of % of sun-like stars have those. For lower mass stars, the number is even higher, maybe even approaching 100%. So there are tens of billions of planets in the habitable zones of stars in our own galaxy alone. But what we don't know about these objects, and what we have yet to learn, is whether any of them possess atmospheres, possess the right kind of atmospheres, whether they actually have water on them as well. And so we're just starting that journey with the James Webb Space Telescope. This is our first facility that will have the ability to peer into those kinds of atmospheres. So one of the first things that we're doing is just asking the question whether rocky planets have atmospheres or not, because in our own solar system, we have a diversity of terrestrial planets, okay? We have some planets that have thick atmospheres like Venus. We have the Earth, which has sort of an intermediate atmosphere, and we have Mars, which almost has no atmosphere at all. There are reasons to think that terrestrial planets around other stars could or could not have atmospheres. And so we're starting to do that. We're asking that first question. As we learn more about that, we'll certainly try to push towards the detection of so-called biosignature gases that are gases produced by life and only by life. These are chemical species that are out of equilibrium with their environment and thus must be constantly replenished, and not by some sort of geophysical source like a volcano or something. But this is a very long road that we're going down, and we're making good progress towards that, but it will require using James Webb to its absolute limit if we're able to do that science of biosignature gases. And really, it will require a next generation space telescope that astronomers are now in the planning stages of that could launch in the 2040s.
Okay, thanks very much. I'm going to actually interject myself here in response to the very last thing that Jacob said, which is, given the length of time it takes to put a project on the scale of the James Webb Telescope together, what kind of planning is going on for the next generation telescope and what do astronomers want it to be? What's feasible and where are we going?
You picked up on something at the beginning of my talk. I mentioned that James Webb was conceived in the late 1980s, right? And didn't launch for more than 30 years after that. And so we've already begun, and we started, more than 10 years ago, actually planning for what will come after James Webb. And there are space telescopes that are coming after. For example, the Nancy Grace Roman telescope should be launched in a few years. That won't really be like a major, huge, large flagship mission like James Webb. So we're really planning towards a mission in the 2030s and the 2040s that would be the same size as James Webb or larger, and would be able to directly image planets, spatially resolve them from their host stars, and particularly do that for Earth-like planets. The mission concept has undergone a lot of variations over the years. It's now currently called the New Worlds Observer. That's the mission concept. NASA is putting together, actually, as we speak, a panel of experts to further refine this telescope concept. It was recommended by the U.S. National Academy's recently led decadal survey. That's every 10-year process that astronomers undergo to plan for the next steps and to make these long-term plans. So it was recommended. It's the highest priority for astronomers moving forward, and we're taking the next step towards designing it. But again, these are multi-decade long projects, and so we take things step by step. And I'm really excited about what James Webb is telling us. We're going to learn a lot more now. The University of Chicago is also involved in the construction of the Giant Magellan Telescope. That's a very important project that could see first light at the end of this decade. That will also, in other ways, advance us towards the understanding of life on other planets.
Great. Michael, do you want to add anything about desiderata from your end of the scientific community?
I will say James Webb and the Giant Magellan Telescope, which will be coming up hopefully at the end of this decade, are both examples of general observer facilities. And one of the interesting challenges that we have to navigate going forward into these next major space telescopes is whether they can be designed in a way that continue to make them general observer facilities that address a huge range of science topics, as you have seen today, or whether it is strategically better to focus in on particular questions and do what the physics community might call an experiment, to have a specific facility to do very specific things. Now, NASA does a lot of that on smaller scales. There are smaller class missions, smaller telescopes that are really designed to address very specific questions. There's a currently functioning facility called TESS that's all about transiting exoplanets around bright stars and cataloging enormous numbers of those. But a thing that NASA has never done, at least yet, is a mission that's at a very large flagship scale that is also scientifically focused in this way. And I think that's one of the debates that will go on for some time yet before that settles down, about whether one can achieve these extraordinary goals while also doing a whole bunch of other very interesting science at the same time. And I don't know where that's going to head.
Great.
It'll be interesting to see.
Okay, so we have another cluster of questions that I think more or less resolve themselves into: have we learned anything yet from the Webb telescope that changes our view of sort of fundamental cosmology and the origins of the universe? And then, as if that wasn't a big enough question, somebody else has thrown in, and has there been any feedback from the folks in the divinity school about that?
I suppose I should probably attempt an answer there. Let me take the second question first. Not to my knowledge, but that may be the limitations of my knowledge. In terms of sort of the impact of James Webb on cosmology, you may have seen a fair amount of news reporting about astronomers being flabbergasted and baffled, and I forget what the other words were, by the fact that James Webb found some rather more massive and larger than expected galaxies at fairly high redshifts, i.e. fairly on in the universe. Well, I I don't think we're baffled or flabbergasted, intrigued, interested. And that's a result of James Webb taking data in regimes where we've had very little information up until now. And so we've been extrapolating into that redshift time space with models anchored in lower redshift data. But I wouldn't say that those models were so robust that the fact that the observations don't line up with them all that well is in some sense revolutionary. It's extremely interesting to see those objects, and they'll be studied in great detail. More broadly, thinking about the cosmos as a whole and the measurement, for example, of cosmological parameters, there's sort of an ongoing debate about the value of sort of the oldest cosmological parameter of them all, the so-called Hubble constant, the current expansion rate of the universe. And you can measure the Hubble constant in various ways. And when you do that in various ways that probe sort of different redshift regimes in the universe, you get somewhat different answers. And depending who you talk to, the tension in those answers is sort of 1 in 100 or 1 in a million, and it's worth paying attention to, because it may be, if that tension is real, to resolve it, we have to have some new physics in the cosmos that's not currently in our models. James Webb is going to provide significant forward progress in many ways on those questions. But getting to that data, getting to that analysis is typically a dedicated multi-year effort of monitoring various things and quite elaborate and very careful statistical analyses. So it's not the sort of result I would expect to see in the first 9 months from a new facility. But it will come, and I think it will be very, very interesting.
A very, very different and more specific kind of question came from somebody who just asked, is the Webb telescope at any significant risk from space debris? Or is it out somewhere where that's not a problem?
So it's out somewhere, and yes, it is. So the observatory lifetime projections include a model for the impacts of micrometeorites. And I will say our knowledge of that micrometeorite environment at L2 is not necessarily completely precise. And disturbingly, to those of us who were paying attention to it, at least anyway, there was an impact with larger and more energetic micrometeorite than expected fairly early in the mission, within the first few months of science operations, that has left a discernible feature in one of those 18 hexagonal mirrors and has very minutely degraded the overall performance of the telescope. Now, the mirror was over-spec'd in part so that it had that overhead to absorb those degradations over time and still perform to specification. But the fact that one of the first impacts recorded was rather more damaging than anticipated is, I would say, a little bit worrisome. It could also just be bad luck. There hasn't been another one of that scale. And I think the predicted rate was sort of 1 every couple of years. And so if there isn't for another year, then it's probably about the right prediction and everything will be fine. But forecasting that kind of risk is a little tricky.
Michael, could you clarify whether the impacts from micrometeorites are asteroidal dust, so natural dust, or it's man-made debris? I think the question was more towards man-made. Right.
Yeah, I don't think there's much man-made debris at L2. If you put it in low Earth orbit, probably a different story.
We've seen that movie, I think.
Yes, right. Somewhat exaggerated timeline, but yes, we've seen that movie.
I find the next question very exciting because it's actually one that I can answer, which is somebody saying, can you get access to this program after it's over? And the answer is yes, we will be posting it on YouTube after we do a little bit of technical cleanup. So getting back to questions that I absolutely can't answer, we've been asked, has the Webb telescope told us anything yet, or is it likely to, that helps us understand the probability of multiverses? I have
No.
to admit, I really don't understand this question at all, so I will just punt it.
Well, the whole idea of multiverses is a very theoretical construct, little connected to the observed universe. I'm a hardcore observer. I will just put my cards on the table. If I can't see it and measure it, I'm not particularly interested in even thinking about it. I have colleagues whose brains work very differently, who think about things with little connection to the details of observations. But no, I don't think at this point one could point to any observation that James Webb has made that has anything to say about the idea of multiverses.
Another relatively specific question. Will the Webb be studying in the dark matter and dark energy areas?
Oh, enormously, yes. I suppose this is me again, Jacob. So gravitational lensing, which I use extensively to study the most distant galaxies, is the result of the fact that there is dark matter in the cosmos. If there was only the matter that we could see in the glow of stars, etc., you basically wouldn't have strong gravitational lensing. The only reason why we see those extraordinarily large, magnified and distorted features of background objects is because there's an enormous amount of dark matter in the foreground lens. And so in principle, you can use various studies of gravitational lensing to extract information about the mass distribution in that foreground lens and hence say something about dark matter. And if you do that on a range of mass scales, which you can do by studying various kinds of strong lensing in various ways, you can extract information about the spectrum of dark matter halos across a huge range of scales, which starts to then tell you what dark matter can and cannot be. In addition, very differently, there are very, very sort of ultra-faint dwarf galaxies around our own Milky Way that are satellite galaxies, which are hard to study even with our largest and best telescopes. And James Webb will contribute significant observations of the few stars in those objects. And they are remnants of galaxy formation at the very low mass scale where dark matter properties almost dominate the outcomes. And so that study will also make significant contributions to dark matter studies and dark energy as well, ultimately, because it's all connected.
Okay, so now we've got another one that I think is more in Jacob's ballpark, which is the Webb telescope likely to tell us anything that would be relevant to the feasibility of terraforming some other planet?
The short answer to that is no. But I think we understand the challenges of terraforming well enough to know that it's extremely unlikely anytime soon. So for example, the atmosphere of a terrestrial planet is the result of billions of years of geological processes. And those processes operate on a scale that far outstrips human industrial capacity. There are only small changes that we've made to our own Earth's atmosphere. The rising amount of carbon dioxide in our atmosphere has changed by a factor of less than 2 from the sum total of human industrial history. Now, that has had an impact on the climate of the Earth, but we're talking about a few degrees Celsius, right? To take something like Mars and to warm it from minus 100 degrees Celsius to a livable temperature is frankly inconceivable right now. You'd have to generate a very thick atmosphere, and there's no way that we can imagine doing that right now. So it's not really a James Webb question, but yeah, I can give an answer to that, which is not feasible, not likely.
Okay. All right, so we've run a little bit beyond our scheduled time. I want to thank the participants and thank the audience. And I will turn things back over to Mark now.
Thank you so much, Ken, Mike, and Jacob, for this great discussion. I've been waiting for this for a long time, so I really appreciate you taking the time to join us tonight. I do want to remind everybody that's here on the program that these programs are put together by the team on the University of Chicago campus here in Hong Kong, and Ken Pomeranz, who moderated the program this evening, spends a lot of time with our team developing content for these online programs. So thank you so much, gentlemen, for joining us tonight. As I mentioned earlier, we have a brief poll tonight for the audience that's on Zoom. And if you're watching us live on Facebook or YouTube, you can leave your answers in the comments and answer the poll question that way. But while you complete the poll, I just wanted to make one reminder for everybody. If you haven't seen the new exhibition at the Hong Kong Jockey Club Heritage Interpretation Center on our campus, again, our staff worked closely with Ken Pomeranz to put together a wonderful exhibition. Since December, we've had well over 1,000 people come and visit this exhibition called Hong Kong Memories, Miniatures and Photographs of Old Hong Kong Streetscapes. It features miniature replicas of Hong Kong streets and buildings, which a lot of people are finding fascinating, and also has some AI colorized black and white photos. So it's a very stunning exhibition, and I hope that you can all join or come and see it. You do have to register on our website, so please do that before you come to the campus to see the exhibition. Make sure you follow us on Facebook, Twitter, Instagram, YouTube, LinkedIn, or on the Yuen campus website so that you can get more information about our exhibitions and our online programs. We will be ramping up the online programs in the coming months, so please stay tuned for those. And for everybody that joined us, thank you so much and have a great night.
Thank you.